Hi everybody, this is your TA Matt. I'm here with a video on recursion explained using the n queens example from class. So once again, I'm Matt, one of your TAs, and I'm making this video mainly because project 1 is heavily related to the n queens example. It uses a lot of the same ideas, and so I'm hoping like an in-depth video here on the recursive ideas in n queens will help you with the project and just understand recursion in more detail, more generally. So yeah, the motivation here is just to deeply understand n queens. In order to do this, I'm going to introduce an iterative example and a recursive example, and I'm hoping this really helps you with your project 1 code and ideas and things like that. So this is not going to be specific code that I'm giving you. I'm just going to be going over the ideas using pseudocode and things like that. So I'll mention the discrepancies between the pseudocode and like the actual code that's posted on GitLab at the end of the video, or maybe a bit as we go along. But yeah, let's see where we're headed here. So I like to start lectures or videos or whatever with some learning objectives, just so you get a feel for what you should be understanding and kind of a metric. So I'm hoping that you already understand the n queens problem, but at the end of the first few slides, you definitely will. And then I really want you to get the high level ideas here. So let me kind of highlight that. Just these high level ideas are what I'm going for. So this is going to be backtracking. If you're familiar with that from the course, that's like the keyword here is backtracking, but we're going to build up to that. And we're going to do that using an iterative solution because I'm assuming you guys all come from imperative languages like Java, C++, Python. And then we'll build up to a recursive solution, which is going to be the focus of project 1. And hopefully you can see the similarities between the two, know how to reason between them, and then how to frame your potential solution for project 1 a lot better. We are going to be introducing a recursive solution to n queens that will be very pseudocodey, and hopefully it just conveys the ideas super clearly. Okay, so let's go ahead and start off with the definition of the n queens problem. It's a pretty simple definition here. The idea is to place n queens on a chessboard of size n by n such that no queens are attacking each other. So here's a 4x4 example. So the idea here would be to place 4 queens that aren't attacking each other. This was done in lecture, so I'll go over this pretty quickly. But let's say we were to change the color to green. Let's say we were to place a queen here. Then this queen attacks these squares, and these squares. And so if you want to place another one, you could only place it here if you're going kind of column by column. And this queen would attack these squares, these squares, these squares, these squares, like this. So this is just showing how the queens move if you don't know chess. But sorry, there's an important observation here, and that is that one queen must be placed in each column / row. So if you look before here, when you place a queen, it's going to dominate its respective column and row. So if we're thinking about how to solve this problem, we're kind of going from the ground up here, trying to build up our intuition, get a feel for it. I'm going to assume you don't really know what recursion is, or maybe you've seen it kind of used in the Fibonacci sequence or like a summation or something simple, but nothing too complicated. So if you're like me, you probably thought of I kind of made a mark there. Let me get rid of that. Okay, so if you're like me, you probably are thinking of iteration here. You can maybe loop through the columns because one queen must be placed in each column. So let's go ahead and kind of start with that, right? So here's like a first pass at like an iterative solution that's very naive, but I think gets across an initial idea here. So for each column in the board state, so kind of this board state is going to capture all of the information about the board. So where the queens are placed, the grid, and what the queens are threatening. In the pseudocode or in the actual code for the class in the GitLab, it is not expressed this way as like a board state object or a variable or whatever. It's kind of pseudocodey. There's like the threats vector / array and things like that you have to manage manually, but I'm just going for ideas here. Okay, so each column in board state, place a queen in the next available row. So let's go ahead and do that. Just kind of see what's wrong with this solution, right? So if I place a queen here, it will cover these squares, and this is kind of how I would execute through this code. So for each column, so we move on to the next column, we'll go ahead and place a queen in the next available row. So for the next column, which is this like C1, if this is C0, then the next available row would be this one, right? Because these two are taken by that queen. So I'm going to use these dots throughout this video to convey dominance by the queen. Okay, so if we place this queen and we update the threats or the board state, then we can see actually all of the squares in column 3 are occupied. And so we can't place a queen in column 3. So, using this code, we'd have to kind of modify it a little bit. But I mean, the best we could really do is skip column 3, right? And go ahead and place something here. So I kind of missed a square, but this is covered by the blue square. So I won't double mark the squares. I think that'll get quite populated. And I think it's kind of clear what's covered by the queens once you look at it for a little bit. But yeah, there's no way to place this third column. So the solution does not work. But I'm a little bit interested in why it doesn't work, because I think this is like a good idea, right? It builds off of this observation we saw earlier where one queen must be placed in each column and row. And then it kind of checks for available rows, right? I kind of have that highlighted here for the next available row. So it doesn't really place in incorrect squares, but it doesn't do something very important. So we saw, so I have this slide prepared here with the entries. We saw that it got stuck, right? It got stuck on this third column super fast. But I'm interested in why this happened. It's pretty obvious, but maybe you want to pause and think a little if it's not immediately clear to you. I'll give about 10 seconds, then we'll kind of continue. Okay, so the reason this happened is because our solution made a pretty bad mistake, which is we assumed if we placed a queen in the next available row, it would lead to a valid solution. I hope this is kind of clear to you, right? We made this very naive assumption that in the following row, we could just get the next available one and that would place a queen there and everything would be cool. Not the case. So this is not a good solution, right? This next available row idea is really not it. Okay, so how do we account for a bad placement, right? So this idea is pretty good, I think, actually, this kind of iterate through the columns idea, but we need to account for when we place poorly, right? So once again, take a couple seconds. I'm assuming you've already seen this in lecture, something similar, so go pretty quick probably, but probably give like 5 seconds and then we can continue. All right, let's go ahead. So the idea is you need to like undo the bad placement, right? I hope that was kind of obvious. So you really want a way to say, all right, once I place this and I tried to move on to the next column, my solution became invalid, right? I could not continue. So I would really like a way to remove, sorry, you kind of hit that there. I would really like a way to remove the queue here, right? And then place the queen in the next column and try continuing with that, because it does look kind of promising, right? Like if you envision it a little bit, you'd place the queen here, and it would cover these guys and then these guys, not this one anymore, right? And this one would be free, so we could place maybe the next queen there, right? We could place our next one here, and that'd be pretty promising. So it'd be cool if we could do that somehow, right? If we could undo our placement. So the way we do that is we can save the state of the board before we make a placement, and then we can revert our placement by recovering the old state. And that would allow us to place our queue here instead, right? We can revert back to our initial state with just this green queue, and then we can actually continue like with some kind of looping structure inside of here to do the next queue. Okay, so this is the key idea. We need to revert, right? Revert a placement, also known as backtracking. So let's kind of go over how we would do that, right? You actually just implemented something that does this, right? Or a structure that we can leverage in Project Zero, and that's the stack. So the stack can kind of hold these board states as we proceed, and we can rely on processing our stack as kind of like a work stack, right? We keep the board states on the stack and push and pop off when we need the old states. So let's go ahead and see what a solution would look like for this. So here's some pseudocode, very rough pseudocode for using a stack to keep track of our state. And I hope you're kind of, if you've seen Recursion before, I hope you can see how this is building up to Recursion, but we'll get there. So I introduced this board stack here, and don't worry if this code is not immediately obvious. We're going to spend some time going over a working example with it. But here's what we introduced. We introduced a work stack that's going to be stored as pseudocode. Just pretend this is like a stack. We're going to push the initial board state to the stack to kind of start things off. we're going to process that stack, right? So we're going to say, while the stack is not empty, so while we have something to process, we're going to pop off the stack. So hopefully you know the pop operation. I know it didn't return in your example or in your project, but for the sake of pseudocode, let's say it does. It's not really that much different. But for each of these board states on the stack, we're going to loop through each available row. We're going to place a queen in that row of the new board state, and we're going to push the new board state back to the stack. Okay, so this might seem like it came out of nowhere. Like, how did I come up with this idea to use a stack? Well, we're going to see it in action here. And then maybe it'll become a little bit more obvious. Okay, so I'm going to push the code over here to the side, and we're going to take a look at what this looks like and how we would kind of come up with this idea on our own instead of just having magical pseudocode just appear before us. Okay, so when we first start off, we have this initial state, right? This is not very interesting. The interesting part is this while loop here that we added. Like, why a while loop and why a stack, right? Okay, so just bear with me for a second. So to start this off, we're going to pop off the stack. So this is the board stack object, and I have this kind of yellow box indicating the new board state, which just is this empty grid for now, right? So it's going to be this empty grid, and we're going to loop through the available row in the column we're at. So this board state will kind of store the column we're currently at. So we're currently at column 0, right? This first one. And we're going to place a queen in each board state. Okay, so this is the kind of the key idea here, and why I hope now the stack is a little bit more obvious, but we're going to kind of continue through this example. So we're currently placing the green queen here. We have this for loop to go through each of the rows. This is very important. Each of the rows, right? So this idea was not present in our previous solution. So we actually need each of these rows when we're working on a column because we don't know which one is good, right? Which of these rows, or question marks, sorry, they're really bad, but we don't know which placement is good for the queen, right? So we actually need to try them all, right? We need to store the state for them all, right? So we can try placing in the first one, and once we update the board state with those threats, we can push that to the stack. It's kind of working through this for loop. And then the second one will be the second slot in the corresponding row, and then the third slot in the fourth slot. And here, notice I'm storing the entire board state, so that includes the threats as well, right? Okay, so once again, this idea of the stack may have seemed like it came out of nowhere, but the fundamental idea was to just get some storage, right? Get some way of storing our decision so that we can come back to it later, right? And I chose to use a stack because you had used one in Project 0, but it could have been a queue or something else as well. The stack, I think, is just most familiar to you, or like most recently used, and it mirrors recursion very well. So we're going to go ahead and use that. Okay, so now if we come back around the while loop, so remember we were in this for loop, we kind of exited this for loop by adding the 4 queens, 1 in each row, so for each available row, and there were 4 of those, so we have 4 things on the stack. Okay, we come back around, and we're going to process the top of the stack. Okay, so we're going to process this board state that's on the top of the stack. And so what that looks like is, sorry, let's go down and pop it off. I kind of had to move the stack down here because we're going to add a lot more things and there wasn't enough space, but the only thing that's different is the stack is now horizontal. So we have this new board state, which is the green queen in the bottom left, right? That was on the top of our stack previously. We're going to now process that board state, right? So we pop that bad boy off, put it in the new board state, and now for each available row in the next column, so we're inserting the blue queen now. This is kind of how I like to delineate the next queen in the second column. So we'll use like the blue queen for this column here. But you see in our new board state, so once again, assuming the board state stores which queen we're working on, this is not the case for the C++ code. I think that has to be like managed manually or passed in via the parameters of the recursive functions, but we're going to kind of build up to something similar to that. Okay, but you'll notice when I went through the available rows here, there's only 2 new entries, right? Because there's only 2 available rows in the following column, just the first and the second. So I think it'd be actually more accurate to switch these board states, because I think you'd actually push this guy first because this queen is on top, like I did first, second, third. Then this is the one we're currently working on. But you'll see now I've generated permutations for the bottom left queen with both of these queen entries, right? Whereas before, I only got one of them. I think, so sorry, the example might be a little different than the example before, but before we had started on the top left queen, but I mean, now we're on the bottom left. It should be, you can just mirror them, right? The order does not matter. We're going to exhaust all permutations anyways. But you can see we now, since we have this like magical for loop here, this key idea of the for loop, right? So iterate through each row. We did not have this before. We're just going column to column, and we didn't have a way of coming back, right? So now we're going to successfully generate all the permutations because we're going to have queens in the empty rows for each column, right? And that's because we have the stack. So let's kind of continue on and see what happens. So now, this loop will finish executing, and we're going to kind of come back up to the beginning of the while loop, and we're going to pop the next entry, which, if you remember here, was this one with the blue Q here. So we're going to work on that one now. We're going to pop that off, and we're going to try to place the next queen, which we're going to color orange. Okay, and as you can see, there's only one spot for the orange queen, this third one. So there's only one available row. So when we get to this for loop for inserting the orange queen, which once again stored in board state using super pseudocode here to just convey the idea. And then we're going to push that to the stack. Okay, so we're going to continue. And now it gets pretty interesting, right? Because we run into a block because we've placed this orange queen, but we cannot place the final queen, which I'll color red, in the fourth column. There's no slots for it. So when we get here, we're going to try to, so there's a couple ways of looking at this. And I think this slide actually conveys it more accurately. So I think we're going to use this one right away. But for each available row here, so there's no available rows in this fourth column. And so this for loop is actually not going to execute, right? So there is no available row. If you take my word for like the implementation here, this available will check to see, if the threats line up for this column. And so we're not going to push anything new, right? So instead, this for loop is going to get skipped, and we're just going to come right back out to the while loop, right? And what that means is we're going to pop. So sorry, this arrow should be here. What this means is we're just going to pop the next state. We're going to pop the next state, which was this one with the Q here, right? So now we're popping that one off because our previous one failed, right? Our previous entry of placing the orange queen here failed, and there were no more slots, right? That was the last thing on our stack. So we're just going to pop off what was there previously. Okay. So now we're back to this queen here, and we'll see that this one is also blocked, right? Which is also interesting. So there's no available rows in this third column here for us to insert into, right? There's no contents, no available row. So we're also going to skip this for loop and come right back out to this while loop again. Okay, so now we're going to pop off what was on the stack at the end of that, and that was this queen on the third row here. So that's our next bet at the solution. So you can see how we're working through the permutations here because of the stack. Because we kept these on the stack at the beginning, we're able to work through all of the permutations, right? That's where the structure, the storage is coming in handy. Okay, so now let's work on our stack with this queue, right? So you can see there's only one slot, which is this one for the blue queue. That's the second column. So it's a green because there's a available row now, yay. And so now you should see how this is going to continue on to lead to a solution, right? We're going to place the orange queen here, and then that's going to cover this square, and then we can go on to place the red queen. So I hope that convinces you that this stack idea works, right? So let's kind of reflect a little bit. This may be a new idea to you, right? Using this stack to save your state to backtrack. But the problem with our initial try was that assuming that like this queen placement would lead to a solution was wrong, right? That this our first try was very presumptuous, but we needed to use some storage, right? Some storage to keep track of what we had tried previously so that we could kind of undo or revert our attempt if it didn't work out in the end. But the problem is we can't like see into the future, right? We're kind of blind going in from column to column. So we have to try, right? We have to exhaust the options before we actually know. So this technique is called backtracking. If you want to look more deeply into this and other external resources, you can look up backtracking. Depth first search or kind of recursion are all very similar here. But I think the most common tough thing to understand is how this like for loop and the pushing works, right? Like why we need to push for each empty row. I hope that was kind of clear in the working example. But make sure you get this, right? This is going to be important going into the recursion. Okay. So let's go ahead and move on to the recursive solution. So I hope that iterative solution made some sense. If it didn't, that's okay. Maybe after we explore the recursive solution and talk about the ideas more fundamentally at the end, it'll make sense. But for this project one, you have to use recursion, and this problem can be solved using recursion. And it's beneficial to solve it with recursion because it's a very elegant solution. And I did cover up a lot of implementation details that get really hairy with the iterative solution. Managing this work stack is like not so fun, and you need to maintain a lot of state, in this board state, or you need to be very careful. If you don't make a copy of the board state when you push it to the stack, you have to be very careful about kind of reverting your changes to a reference, which you have to do with recursion, but I think it's more easy. It's easier done with the recursion. So let's go ahead and talk about recursion a little bit. So most languages support this feature called recursion, where you can call, like a function can call itself. And the key idea that I'd like to introduce is using this call stack, right? So this call stack that is given to you when you make a recursive call is going to mirror this working stack that we created ourselves. And that's kind of one of the main reasons I used a stack in the previous example, and kind of wanted to run through that. And it's going to analog that example. But instead of using an explicit stack, so instead of having to like create that board stack structure, we're actually going to leverage the parameters on the call stack, which I hope you're familiar with, but we're going to get into the details with a very simple example. And so anything you would have wanted to store on this board stack, like previously, like it was kind of we were storing those board state objects, can instead be passed as parameters to the recursive function. This is very important, very, very important. So these parameters serve as the context under which the recursive function will execute. Okay, so let's go ahead and look at a very simple example, and then we're going to generalize over to the n queens. Okay, so the example I'd like to look at is a sum implementation. So the one on the left is an iterative version of sum. It simply loops through n numbers, adds them to s, and then returns s. And then on the right is a recursive equivalent, which will take a number n. If n is 0, we're going to return 0. Otherwise, we're going to subtract 1 from n, and then we're going to pass that through to our to the recursive call, right? This will be 1 less. We're going to subtract 1, and we're going to add that and return the sum. And so this will return the sum in 2 different ways. I'm using a variable here just to make a point that we'll see shortly. Okay, so the most important thing to understand is what goes on in the call frame. So it's very important to understand this when you're dealing with recursion. So let's look at the iterative example first. So in the iterative example, we're going to call, let's say, sum3, right? We have some caller who's calling sum of 3. So whenever a function is called, there is a stack frame allocated for the function. And on the stack frame are some interesting things like parameters, which means n gets a slot on the stack frame, and locals. So s gets a slot on the stack frame. And there's something called a return address. Also here, some other pointers that are important for the caller, but the only things we care about here are the parameters, the locals, and the return address. So what happens when we call sum with 3 is this slot allocated for n will get the value 3, and the slot allocated for s will get the value 0 at the start, right? Once we go to this initialization here. So once we get through this loop, we're going to kind of run through this loop a few times, right? 3 times. And this value here is going to get incremented each time. Sorry, I didn't mean to delete that. So this value sorry, I hit the wrong button. This value is going to get incremented each time we go through the loop. And so the first time it'll be 1, and then, sorry, kind of white. It'll be 1, and then 2, and then 3, right? So, we can maybe cross off the 1. Once we go through the loop, it'll be 2, then 3. But you'll notice it's on the same spot in the call frame. And once we return, this return value is going to get pushed. So quick caveat that if you're dealing with an x86 architecture, you can pass parameters using registers and not on the stack. So if you've taken something like 51 or an assembly course, that's just a quick caveat. But the ideas are the same. It doesn't really matter where it is, but I think the stack frame conveys the idea correctly. Okay, so onto the recursion, which is more interesting. So what happens here is when we call sum of 3, we get a lot of function calls, right? So let's take a look at the frame here. So there's first going to be a frame allocated for sum 3, right? And so once again, there's going to be a parameter slot and a local slot. So the parameters I care about are n, which is going to be 3 at the start, and then s, which is going to be n minus 1, so that's 2. And so there's also going to be a return address right here, return address. And that return address is going to point to this slot because that is where I called the next function, right? So when I call sum, there's going to be a return address pushed to the stack. I guess more accurately, the return address for this call will be pushed to the call frame for the next one. So let's go ahead and write that in. So we're going to call sum of 2, right? Because s is 2. So let's kind of point here, break this off. So when I call this, the return address is going to be pushed to this call frame just to be more accurate. There's going to be a slot for n again, which is 2. So let's keep my slot there for n, and then s, right? And so this is going to repeat. So we have the return address again, which is going to point to the same slot again. And then we're going to have sum of 2 and sum of 1, right? Okay, so let's go ahead and go down here. Sum of 1 and sum of 0. So we're going to do, maybe mark this off. So sum of 1, n will be 1, right? And then the s will be 0. And then for sum of 0, the n will be 0. And what is interesting is at this point, so there's also a return address down here. So what's interesting is at this point, we're going to hit this return 0 call. Okay, so we're going to hit this bad boy right here. And what's going to happen is when we hit that return 0, we're going to pop this return address off the stack, and we're going to return execution to the address that's pointed to, which is here. And so that's at this call frame, right? So this is going to stop, this is going to finish executing. We're going to turn execution up to this guy, right? And we're going to use these values of n and s, right? So we have a return value of 0, which is going to get added to n, right? So we're going to have 1 plus 0, and we're going to go ahead and return that to our caller, which is sum of 2. And then that's going to get added with his n value, right? Which is going to be 2 plus 1, and that's going to get returned to our caller, which is sum 3. Because remember, these are all on the call stack, right? And these return addresses are going to return execution to where it left off when we called the inner function. And the key idea, so the most important idea to understand, is that these calls do not go away, right? This sum of 3 is still there, and it's still going to return to execution once these are finished, right? And then this guy is going to return n plus 3, right? So 3 plus 3 to his caller, which is 6, and that's how we get the sum of 3 back to our caller. Okay, so what I really want you to understand is, there's a lot of detail here, but what I want you to understand is the call frame for your caller does not go away, right? So these locals and parameters are preserved on the stack, right, in the call frames for each of the functions, right? Okay, so the key idea here is that we can use the stack via call frames to store context. All about context. So if you notice, the context when I'm executing sum of 2 is different, right? It's the same function body, right? The return address points to the same spot, but the call frame context is different, right? The value of n is different and the value of s is different. And that allows me to use execution, so use the same code, but under a different problem, right? Under a sub-problem. We'll see this later, a sub-problem, right? So the sub-problem for sum is just subtracting 1 and then getting the sum of that, right? So sum is defined recursively, pretty trivially, where sum of s equals 1 plus the sum of s minus 1, right? Pretty trivial. But the sub-problem is just subtracting 1. And I hope this visualization allows you to see that the sub-problem uses our existing code by changing the context in the call frame, right? With the locals and the parameter, right? Those are different. The parameters are different. Yeah, parameters are different, right? And then return. So it's also important to know the return addresses are all on the stack. So execution will resume at the place where we left off in the given context, right? Okay. So that's a lot to understand here, but very important going forward. Okay. So now maybe take a breather here. If this is all, if this is a review for you, we can forge ahead. But this is kind of a lot to understand. Make sure you really understand this. Make sure you look at external resources. Make sure you post on EdSTEM if this isn't clear, because this is very important when you're doing recursion. Okay. So now back to n queens. So how can we solve n queens recursively? So the way I've elected to convey this information is just by giving you kind of a working example and then proving to you that it works and then showing my thought process for coming up with it. Because my understanding is that you're kind of new to like this exhaustive search recursion style. And so, maybe you can take a pause and try to think of one yourself. But I don't know. I don't really think it's very useful right now. I'd rather just spend the time looking at the core idea. Okay, so the core idea here is that we want to mirror that stack usage from our iterative solution using the call frames on our call stack, right? And so how can we do this, right? Before we saw that a sub-problem for sum minus 1 that we can solve is just subtracting 1 and looking at the next number, right? Well, for the board state problem, it's very similar, right? The idea was that you place a queen, right? You place a queen in a row, and then you have your sub-problem just like sum, right? Once we place a queen, we have an updated board state that instead of using an explicit stack, so there's no explicit stack, right, as we had before in the iterative solution. Instead, all we do is we pass the updated board state to our function recursively. And that board state will be updated with the queen placement. And once again, we have to do this for each row, right? Okay, so it's totally cool if this doesn't understand, but this is the key idea in the solution that I'm gonna work through an example and we're gonna revisit at the end, but this is the idea to understand. Okay, understand this for project 0. Or project 1, sorry. Okay, so we're going to go through the example now and see how this works. Okay, so let's look at the call stack. I'm going to use pictures to kind of represent what we did with the sum. So the caller of this function is going to call solve n queens recursive with an empty board state, right? And so that empty board state is going to be a parameter on the call stack. Whether it's a reference or a copy is up to the implementation. Both can work. But we're going to call with the intention to place a green queen or a queen in the first column, right? So that, once again, that's part of the context, right? That's part of this board state context. It holds a lot of things, right? I'm depicting it visually with a very simple grid, but it holds a lot of info, right? It holds the current column, the threats, right? And the grid, right? It holds all that information, but I'm only conveying it with a picture for simplicity. Okay, so let's look at execution here. So this blue arrow is going to be the currently executing function because we're going to add more function calls. So we're going to execute this with a blank board state. And we're going to loop through, we're going to start this loop because remember, we care about all of the columns, right? Or sorry, all of the rows in a column. As we saw in our primitive example, we can't just do one row placement, right? If we're going to properly exhaust through all of the options, all of the permutations of queen placements to find good ones, we need each row, right? Okay, so we're going to go ahead and place that green queen in the first row, and then we're going to call recursively with the intention of placing a blue queen with the updated board state, which now has the first queen placement in this for loop. Okay, so let's take a quick pause, and I'm actually going to quickly grab my mouse so we can go back to what our iterative solution looked like at this point. Okay. So a key difference is that at this point in our iterative solution, we actually went through the entire for loop, right? We went through this for loop, added all of the states here, and then we processed them from the top. That's different from right now, because what's happening is we're going to kind of go in a more depth first manner, right? We're going to go into our for loop, and then we're going to nest our execution. We're going to call the next recursive function. So here's our call stack, right? We have another call in the call stack, like we had for sum. And we're going to now be executing within the context, right? This context, right? So this context is going to be executing. And remember that on the call stack, we have a return address pointing to the for loop in this guy. So there's still a return address pointing to that for loop in here, right? It's going to be important later on. Okay, so we have a board state here with the green guy. And now we're going to just execute with the intention of placing the blue queen, right? Okay, so we're going to place the blue queen now. This is the first available placement, so we're going to go ahead and place that. So execution is still in the blue, but we're about to make the recursive call to now place the orange queen, which, as we can see, is gonna fail. But remember, there's still return addresses pointing to these guys, right, with our context, with a different context. That's why I have these here. Context is different. Context, important. Okay. So once we get to this orange execution, there actually is no available row, right? So something that's interesting here. So I guess I kind of made a slight error on these slides, but in the previous example, we were checking available rows. But in this case, we're just going to try placing in the rows, just in this example, in this use of the recursion, we're going to place in the row and detect if it failed, right? So yeah, the pseudocode might be a little unclear now that I'm kind of looking at it again, but the idea is there. And the idea is that we're going to try to place in this column. And the idea is if we fail, then we want to get out, right? We want to return false because we don't want to continue, right? We do not, no recursive call. So we do not want to make a recursive call in the case that the placement fails, or, like in the iterative solution, we had a protected for loop. In the case where the for loop, we want to make sure we don't go into another recursive call, right? So this will be very important for project 1 as well. And what's interesting is when we return false here, that's when we pop this context off of the stack. So remember, we're in this orange context here trying to place the orange queen. When we fail the placement, that's when the pop happens, right? And what happens when that pop happens? The return address that's in that context is taken, and we come back to the blue execution. So this is where, in my experience, I see the most students confused about how this solution works. So take a lot of time here, because this is the crux, is understanding that when this fails, this inner call fails, we come out of the inner call. So remember, this is our call stack context into the blue execution that we were at previously. And this orange call is going to resume execution here, but that's really just coming out of the for loop. And so typically you'll see some cleanup code here, right, to clean up the state, but this is pseudocode, and I can assume these board states are copies, and I don't need to clean up if it was a reference. But we come out of that execution back to the for loop, and we're going to try placing a different blue, because that blue did not work, right? So we're going to try placing in the next slot, which would have been here, right? This next slot here, and we're going to cancel that, and then that would have got put on the stack. We would go into the orange, and then we would place an orange, here, for example, and that wouldn't work, and yada yada. We'd come all the way back out to the green and find a new green that would work. like we did with the stack based. Okay, so this is the very important part to understand, this transition, right? This failure case where the column was populated and we have a return false in the fail. I think this logic is a little messy. I'm sorry about that. But the idea is essentially that if the placement in the row fails, like we couldn't place a queen, we need to get out, right? We do not want to make the recursive call for the red queen. Okay. And then once that fails, we come back out to the blue and we are still in the for loop, right? Still in this for loop, right? And so now we're going to place the next blue in line, right? Still in the for loop. This is key. I'm stressing that, right? We're still in the for loop, going to place the next blue. And then I hope execution is kind of clear from there. Okay, so let's kind of look at the final pseudocode for this recursion. So what's interesting is I didn't do the base case initially because I don't think the base case is useful for conveying the idea until you kind of really understand the subproblem here, which is place a queen and then resolve the board state after that, placing a queen in the next column. Okay. So the base case is just to check if the board state is full or if there are n queens in the columns and you succeeded. That's kind of in addition to what we've already had. I made this queen kind of rainbow here because it's going to depend on the board state which queen we're placing, but essentially you go column by column. And then there's an interesting spot here, which is kind of important, this if check, right? So it might, so once you come out, right, you need some way of determining success. So if you kind of think about how these recursive calls are going to go, let's go here. I'm just going to name it solve for short. So we're going to solve with the green queen, if you remember, right? And remember, there's going to be 4 of those, right? So there's going to be 4 green queens. Sorry, I don't actually like the way this is turning out here. So maybe I'll just write or solve. Here we go. So we'll solve, and then these will all be calls. I'll just kind of shorthand it. So there's going to be 4 solve calls with green. And then this green is going to make some additional calls for blue, right? And then this blue is going to make some additional calls for yellow, which might not work out, but eventually, we're going to come back out here to one of these other rows. So like, let's say this was green at row 1, and this was row 2, and this is row 3, this is row 4, and this is kind of blue at row 2. Well, that doesn't make sense because row 2 will be populated by attacking green, and row 4, and then kind of this yellow is like row 4 and row 2 or something, right? You kind of get the idea of how these calls will work out, I hope, by now. Okay. So then let's say one of these works out, right? So it actually succeeds. And so we found that this one here, row 3, I don't know, I'm just making these up. They probably don't make any sense. But let's say this worked out to the solution. Once this happened, we had that, it was clear the return false case, but when the return true, we also want to percolate that return true all the way back to the caller, right? So we need this return true to come back. So this true, 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 and that's when we know we're done, right? And we don't need to execute any of these, right? So this return will save us from executing anything further. Okay, so that was a lot, right? This is a very hard, I honestly think this is a very hard concept to understand. I think the video is kind of clear. I think there's a few maybe snafus here and there, but take some time to really let this sink in. And I don't expect it to be easy, right? Really gonna have to play with the diagram, the recursive calls, and see how they work out. But the key idea was that we leveraged an implicit call stack, right? Using recursion. So we use that implicit call stack instead of the explicit stack, right? And so for problems like this, the solution is pretty elegant, right? I think this is a little messier than it has to be, but it does convey the ideas, and it's very simple, right? There's no work stack, nothing, you don't have to manage a stack or anything. It just all happens transiently by the call stack, but it is hidden, so it is hard to understand. Okay. So after you've solved a lot of problems recursively, you'll start to get a feel for defining them recursively using subproblems, this idea of subproblems. It's pretty common. You'll hear it a lot when people teach recursion. Subproblem. So let's revisit the n queens. I want to kind of show how you'd approach this using the subproblem idea. Okay, so when I would solve something like this, I think initially, what does it mean to make progress, right? What does it mean for context to change? Remember that call stack context to change. What does it mean? In this problem, it's placing a single queen and updating the threats corresponding. So you place a queen, then update threats, and that's how you indicate context change for this problem, right? For the sum problem, it was very easy. The context change is very easy to see. It's just the starting value, right? It goes from 3 to 2 to 1. That's the context that's changing. But the observation is that if you have a function that can place a single queen, you can just call it repeatedly, right? N times. So recursion is actually just another way of looping, right? Any problem that can be implemented with iteration can be implemented with recursion. They are both just looping structures. There's nothing to be scared of. It's just the implicit handling of the stack that's really confusing and really hard to understand. But some languages don't even have for loops, right? C++ allows both recursion and for loops and while loops to be permissive and accepting of different programming styles. But more restrictive languages maybe only have function calls, maybe not even for loops at all. But let's go ahead and continue here with defining n queens recursively, from the top down, right? We kind of showed a bottom up approach where we can, get this idea of a stack and then work into the recursion from there. But typically you'd solve these from the top down. But the observation is that when you go to pick a queen square here to solve the subproblem, you don't know which one leads to a valid board state. So you actually have to try them all in the row. And that's kind of where you come up with this idea of this for loop for the rows, right? For each row, you do not know if it's a valid solution. So you have to try for each row in your subcase as well. Each subproblem has to try each row. And that's where this idea comes from. This for loop with the recursion. This is going to be new, I think, for most people. But like not knowing for each permutation, right? This is how you generate permutations. Generate all permutations, right? You have these 4, and for each of these 4, you're going to have to generate, the open squares, right? So I hope that kind of makes sense. And then after that, I like to think about the base case. Maybe some people like the base case first. If that is for you, then maybe you think about what does it mean for your problem to be finished. But I think it makes sense to think of the decomposition, the recursive decomposition, and how the context change, right? I'm all about this context idea. How do you update the context between recursive calls so that you can leverage your existing code? And I hope it's very evident how that was analogued by the iterative implementation where the context was stored explicitly on the stack. Okay, so there is release code. It is not going to be anything like you saw in this video. It's all getting the details right in C++. But the core ideas are the same, right? The core ideas are there, and I hope it's easy to see how it's translated, right? The most stark difference is going to be that it's using real C++, not Matt's weird pseudocode. And the threats array, and there's going to be some like management, right, using parameters and not this simple board state, right? It's going to be a lot more than just a board state object. But I hope the ideas are now clear, and I hope this was simple enough to convey them. This is like as abstract as I could get to the core ideas here. But in general, my advice is that it's much easier to debug when you have a crystal clear implementation idea than when your ideas are foggy and you're trying to hack on the implementation as well. So I encourage you to do things like I did, which is write pseudocode out and then work through examples and see how the permutations are generated. Okay, so now what does this mean for your project 1? I hope if you've read the project 1 write-up, you see a lot of similarities now, but here are some questions to get you started if you don't. So which of the two of these equations are easier to generate a mapping for? Think about what it means to generate a map, what a valid mapping looks like for this equation, and what one looks like for this equation. Which one took fewer steps? Which one was easier? So can you think of how to define this problem recursively? How do you make one step of progress towards your goal such that you can reuse existing code under a different context, right? So what is the context for this problem, this project 1? Remember, for n queens, it was placing a queen and then updating the board state. And that was our new context, right? And then we generated permutations from there. There's a way to do it for project 1, but you're going to have to figure it out yourself. And does this recursion with for loop, this structure, right? This exhaustive permutation structure. Is that making sense? Okay, so that was a lot for this video. Please let me know on EdStem which concepts weren't clear, and I can elaborate on them in a follow-up post, or you can post more particular questions. So that's about all I have. Once again, I'll be in the Open Lab this week for further questions, so feel free to stop by.